Hello everyone. In this video, I would like to explain the solutions of project number 2, which are on chapters 4.5 through 4.8. Chapters 4.5 and 4.6 are on the graphing of trigonometric functions. The first few questions in this project test our knowledge of the different properties of the trigonometric functions and their graph. The first 3 questions here are asking about the period of the different trigonometric functions sine, cos, and tan. What do we understand by the period of a graph? A period of a function is the length of the interval within which the function has unique y values. For example, let's draw a picture of the sine graph on the xy coordinate plane. We have 0 at the point of origin, and along the positive y-axis, let's mark up to 2 pi, correct? And we have positive 1 on the positive y-axis and negative 1 along the negative y-axis. Those represent the range values for the sine and the cosine function. So for the sine graph, this is how it's going to look. It starts at 0 radians from 0. At 0 radians, sine has a y value of 0. It goes up all the way to 1 at pi over 2, then turns around and drops to 0 at pi units, and then drops below the x-axis all the way to negative 1, and then goes up again to 0 at 2 pi. So within this interval of 0 and 2 pi, which has a length of 2 pi, the graph has unique y values. Beyond this, the y values repeat themselves. The pattern of the graph repeats itself to the right of 2 pi or to the left of 0. So that length of the interval within which a function has unique y values, distinct y values, is known as the period of the function. For the sine function, that period is 2 pi. It's the same for the cosine function. Cosine function also has a period of 2 pi. As far as the tangent function is concerned, its period is just pi units. That means the tangent function will have unique y values within an interval of pi units. Now, the reciprocal functions, the reciprocal of the sine function is cosecant. That will also have a period of whatever the sine function has. So the cosecant and sine have the same period of 2 pi. The same is true for cosine and its reciprocal, the secant function, that too has a period of 2 pi, and the reciprocal of the tangent function is the cotangent, that has a period of pi as well. All right, now that's about the period of the different functions. The next set of questions ask about the asymptotes of the functions. There are just 4 functions to which the asymptotes apply. The sine and the cosine functions do not extend beyond negative 1 and positive 1. They are continuous functions. Therefore, asymptotes do not apply to the sine and the cosine function. However, they apply to the other 4 trigonometric functions. What are asymptotes? Asymptotes are certain locations along the x-axis where the function will become undefined. And all 4 of these functions become undefined at certain points. We have to determine at what points the functions become undefined, and at those locations will the asymptotes lie. The question is a fill-in-the-blank question. It says the graph of tan x has asymptotes at what multiples of what? Now, to answer questions like this, it's best to first draw a figure of the unit circle. So I'm going to draw a unit circle here, and it'll be easy to determine the asymptotes of these functions. However, before that, let's write down what the ratio of the tangent function is. Tan of theta is equal to y divided by x. Now, we have x here in the denominator of the ratio. When does a function become undefined? When the denominator of its ratio becomes a 0. At those locations, the functions will become undefined. That means the y value will either go up to positive infinity or go down to negative infinity, correct? That's what undefined means. Now, if we can determine at what locations, for what angles x would be 0, we will know at those points tangent will be undefined, and that's where the asymptotes will be located. So here I'm drawing a picture of the unit circle. Right, let's draw a unit circle here, and we have our quadrantal angles: 0 at positive x-axis, then pi over 2 on the top, then we have pi, then 3 pi over 2 at the bottom, and then finally when we come around to the positive x-axis again, after making one cycle, we get 2 pi radians, correct? These are the quadrantal angles. Now, when we make an angle, where do we get an x value of 0? So starting from the positive x-axis, when we come to an angle of pi over 2, x is 0 at this point, correct? At pi over 2, x is 0. There's no horizontal displacement. Pi over 2 is located along the y-axis. At the y-axis, x is equal to 0. So at pi over 2x is equal to 0, if we make a wider angle and come around to 3 pi over 2, x will be 0 here as well, because again the angle terminates on the y-axis. On the y-axis, x is 0. So at pi over 2, let's list our angles. At pi over 2, x is 0. At 3 pi over 2, x is 0 as well. And if we come around again and make another angle on the y-axis, that would make it a 5 pi over 2 angle. So 5 pi over 2. And then if we come around and terminate again along the negative y-axis, we get 7 pi over 2 radian angle. And we can keep going in circles and end up with 9 pi over 2, 11 pi over 2, 13 pi over 2, and same thing with negative angles as well. So negative pi over 2, negative 3 pi over 2. That's where x would be equal to 0. Our tangent ratio would become undefined, and that's where our asymptotes would lie. Let's look at the multiples here. We have 1 pi over 2, and then 3 pi over 2, 5 pi over 2, 7 pi over 2. All these multiples are odd multiples. These are all odd values. We are multiplying pi over 2 by an odd number. Therefore, the answer for this question for the tangent function, the asymptotes are at odd multiples of pi over 2. All right. So this is how we can figure out, using the diagram of a circle, where the asymptotes could lie. The next question is asking about the cosecant function, where its asymptotes would lie. First, write out the ratio for cosecant. Cosecant is the reciprocal of the sine function. What was the ratio of the sine function? It was y divided by r. Therefore, for the cosecant, it would be r divided by y. So here y is in the denominator. So wherever y will be equal to 0 in the circle, cosecant will be undefined. So again, let's look at the same picture. Y is 0 whenever we have an angle along the positive x-axis or the negative x-axis. So for a 0 degree or 0 radian angle, y would be equal to 0. There's no vertical displacement on the positive or negative x-axis. So at this point, y would be equal to 0. So let's start listing our angles. So at 0, and then when we come around and stop at pi, which is the negative x-axis, we would have y equal to 0. When the angle terminates on the negative x-axis, we have y equal to 0 again. And if we come around and again stop at the positive x-axis, we make an angle of 2 pi. So at 2 pi, y will be equal to 0. Come to 3 pi, y will be equal to 0. Whenever an angle terminates on the positive x-axis or the negative x-axis, you will end up with y equal to 0. So 4 pi, 5 pi, 6 pi. On the negative side, it would be negative pi, negative 2 pi, negative 3 pi, and so on. Y would be equal to 0 for those angles. Therefore, cosecant would be undefined. So again, what do we notice here? We are multiplying pi by integer values: 0 times pi, 1 times pi, 2 times pi, 3 times pi, and the same on the negative side as well. So pi's are being multiplied by integers. When that happens, we call that at integral multiples of pi. Not pi over 2, it's pi. All right? So that's the answer for cosecant of x. That's where the asymptotes of cosecant would be located. The next one is secant of x. Again, write out the ratio for secant. Secant is the reciprocal of the cosine function. The ratio for cosine was x divided by r. Therefore, for the secant, it would be r divided by x. Now, here we see x again is in the denominator. So, wherever x becomes 0, secant would be undefined. And that's the same as what tangent had. Therefore, the asymptotes of the secant and the tangent function will be located at the same position, odd multiples of pi over 2. So as far as asymptotes are concerned, secant and tangent go hand in hand. Let's look at the cotangent function. What is the ratio for the cotangent? Cotangent is the reciprocal of the tangent function, agreed? So tangent had y over x. Therefore, cotangent would be x divided by y. What do we have in the denominator? Y. That means whenever y becomes a 0, cot would be undefined. And that's where the asymptotes would lie. Let's determine for what angles y would be equal to 0. It would be the same as the cosecant function, correct? For cosecant also, we had y in the denominator. For cot, we have y in the denominator as well. Therefore, they go hand in hand. So it would be integral multiples of pi. All right, integral multiples of pi would be where the asymptotes of the cotangent function would lie. All right.